want to do
all right, I think we're good to start. Last week I posted an assignment on Gradescope about the presentation, asking you to submit a 3 to 4 sentence explanation of your presentation. Only 15 people did it, which is kind of disappointing considering it's like a 5-minute assignment. Might release it today again with a deadline until midnight tonight, so if you forgot about it, we'll extend the deadline until midnight tonight. After class, I'll get on that. Submit it then. It takes 5 minutes, and it's probably like 2 to 3% of your presentation grade, something like that. It shouldn't take you long at all. Just get it done if you can.
You might want to mute, or and also silence your speaker.
Okay.
All right, we're good.
Okay. Yeah.
Wait, does everyone in the group have to submit PDF?
I believe you can just click that or add group members. So do that if possible.
If one group member did it, we'll mark it for all of you guys.
Yeah. But if you can just press add group member, it's a bit easier. Okay. Any question on anything course organization, Project 5, or kernel stuff, what we talked about last lecture? Okay. So the Project 5 is due April 24th, so if you haven't started it yet, get on it soon. We are dropping a couple of challenges, but make sure it's not Project 5 Challenge 3 because you're going to be reusing the environment you set up in Project 5 Challenge 3 for Project 6. Shouldn't be too long of an assignment, but just get it done because at least the environment is going to be necessary again for the next project. Yeah, by now I hope that you've at least started to work or at least think about your presentation and what you want to do. As for the presentation dates, these are the schedules. We'll be uploading the slides to Moodle. Otherwise, you can take a photograph, whatever works for you, or remember it. The schedule lists 3 days for presentation. We currently only schedule people for the first 2. If we need more time, we're going to go into the 3rd day as well. Otherwise, we're just going to spend the 3rd day on final review or just talking about security industry in general and what kind of job prospects this class or what kind of jobs this class might lead into. Yeah, so for today's content, we're going to talk about,
How much time do we get for our presentation?
About 10 minutes.
Well, about or 10 minutes? Like, we have to do this precisely, right?
You can say 10 minutes plus questions.
Okay, I think we'll divide up the number of teams and give you a precise number, and you really can't go over, right? So you should practice your presentation because other people won't get to go, right? So we really have to strictly enforce that.
We do have some extra leeway with the 3rd presentation class we counted in.
Okay.
So if people go like 12, 13, it's still fine. But just if it's around 10 minutes, I think we're good.
Okay.
We have around 6 or 7 groups presenting a day currently scheduled.
And we're 75 minutes?
Yeah.
Okay, should work out. But I really encourage you to practice your presentation at least once. Should only take you 10 minutes.
Any questions on the presentations? If you still have questions, if maybe your topic is adequate, or if what you have planned is fine, or any questions about how you should be doing something, you can come talk to us after class. Yeah.
Just a real quick question. I tried looking online the other day for a specification for the project, the presentation itself. I couldn't find it. I don't know where to find that.
We didn't release a specific rubric. It's a bit hard to make one because the presentations are kind of very different depending on what you do. Some projects might have a very strong practical aspects to it. For example, if you're one group is working on embedded systems, they have a practical aspect of desoldering the chip, getting the firmware off it, and so on. Other groups might have a much more theoretical project in learning about how CPU vulnerabilities work and then presenting about that. That will not have that much of a practical aspect, for example. So it's a bit hard to set up a rubric. If you have questions, I would say maybe just come talk to us. Yeah, I'm mostly just looking for something that kind of goes into technical detail of your project and yeah.
Is there any way we can get a camera hooked up to the projector?
What do you mean?
Just something, if we have a piece of physical hardware that we want to show, that we want to put on the screen so that people can see it, would there be some way of doing that?
Well, I mean, if your laptop has a camera, you can hold it up to the camera.
Yeah. I mean, I guess that would be awkward as hell, but it could work.
Yeah, after someone figure it out.
A lot of rooms have something, which is why I was asking.
Oh, like an Elmo? Is that
Yeah.
what it's called? No, we don't have that.
No, that's kind of a problem.
I think there's one in the next room.
Yeah, there is one in the next room.
Yeah.
It's a pretty small class, and you can also just showcase
Yeah,
it
you
without a
can show and
projector.
tell and pass it around. What are you going to show?
Something roughly
we-
the size of like a phone-ish, with a
Yes,
display yay big.
we have a game console that we are hacking physically.
I think let's talk after.
Okay.
Okay, anything else on the projects? Okay, so for today we're going to talk about how you can actually debug a Linux kernel. We're going to talk about some important files and instructions that are going to be relevant for basic kernel exploits. We're going to talk about some applications of kernel security, apart from exploits such as rootkits or custom drivers you may want to write. We're going to talk about kernel bugs, some mitigations that are used, and then 2 techniques, buffer overflow, or how you can exploit a buffer overflow with no mitigations, and a heap use after free vulnerability. Project 6, we originally intended to have a buffer overflow challenge on it, a kernel buffer overflow. We ended up deciding against it, mostly because we only have 2 lectures per kernel, so we can only have time to cover it more from a theory perspective, so your exploits would have been mostly just copy-pasted from online tutorials, which we don't think is that valuable. So we're going to assign a reading that you should do on how it actually looks. We're going to look over an exploit today, but in your project, you're not going to be writing a kernel exploit. In Project 6, you're instead just going to be reverse engineering a kernel driver and interacting with it to get the expected output. And the other 2 challenges for Project 6 will be focused on fuzzing, which is the topic of the next lecture. Yeah. So first of all, debugging, it's very simple if you're using or setting up your kernel environment using QEMU, which is the setup we recommend for the project and what we're handing out in the launch scripts and build scripts. The only thing you need to do is add a -s argument to the QEMU launch script, which I believe should already be in the launch scripts that you were given for Project 5 Challenge 3. Then you can run GDB on the VM Linux binary, which is basically an ELF binary of the Linux kernel. And then with the -s flag, QEMU opens up a port 1234 by default that you can then connect to from your GDB terminal, and then you have your debugger running the kernel. That's pretty much all there is to it. Let's look at how that would actually look.
Can you zoom in?
So if you look at the launch script, if you looked at Project 5 Challenge 3 yet, that's pretty much exactly what you have. It has the -s flag here, which indicates that QEMU should open up the port for debugging purposes. Another thing that I would recommend is to comment out your pwn debug script, because the GDB extensions such as pwn debug or Jeff, they all have issues debugging kernels, and it gets very, very slow, and it's just better to run base GDB when you're debugging kernels.
GDB tech NX will do that, by the way.
Okay, yeah, or that. Good point. Okay, so let's see. Looking at the file system. Okay. So this is the program we're going to be debugging in this case. It's a very, very small program. Basically, Zors AXEAX moves 0x27 into racks and then calls syscall. This executes the get PID syscall, which just returns the process ID. Basically, as simple as you can make a program, just 3 instructions. I already copied that over onto the file system, as you can see. So now we can launch the kernel. Okay, we are running. We can open the second terminal. In it, we can now run object dump onto the get PID binary to find the address, which in this case is 0x401000, and then use GDB to connect or to attach to the VM Linux binary in the Linux directory. Okay. And then select target, remote, 1, 2, 3, 4 to connect to the port. And we're now attached to this, and we're in our GDB port. So now if I type something in the above terminal, I just type ls and enter, nothing is happening because GDB stopped the process. Once we press continue in GDB, this actually resumed, and as you saw, it just executed the ls command once I continued program execution. So it did buffer the ls, just couldn't execute it because it wasn't in pause state. So we can press Control C in our debugger terminal, and we'll get back our GDB prompt. So let's set a breakpoint. I believe, was it this, the address that we were looking for? Let's continue execution and execute the get fit process, and we hit our breakpoint. If we print out the next 5 instructions, we can see that this is our small program, and afterwards there's this garbage. And so far it's pretty much as if we were debugging a user-end process. This command, the display command, pretty much just says that whenever I press next, it executes this command again, the x/5i_RIP, just because I don't have clone debug's context or window here, I use this instead so that the instruction are printed. Let's move step 2 instructions. And we're now on our syscall instruction. Once we execute the syscall, if you were running your debugger userlet, you would just step right past the syscall and you would be on the next instruction, which in this case would be this here. In this case instead, since we are debugging the kernel, we can press SI, and suddenly we find ourselves in the kernel address space. Any questions so far? Does anyone recall what happened, or what do we expect to see now? What should this be doing? Yeah.
Well, if it hasn't already, I'm assuming it's going to swap memory maps to bring the kernel in.
Mm-hmm.
Then it's going to look up, then it's going to look up the syscall number in the syscall table and invoke that.
Yep. I'm not going to walk through all of that because that's a couple hundred instructions, and it's actually pretty long. It's part of the reason why syscalls are so expensive. So the main parts we're going to be looking for here are first that we save our state. So our register state, our stack state, we saved all of that off. So once we return from kernel space, we still have that. Then we swap into kernel space, we execute our syscall, and we restore our state and return back into userland, into the program we're in before. And the next instruction was invalid, so this would probably just result in some fault after we return. So this is what we're expecting to see. So let's start stepping through. It does some operations, saves some values, and now it starts pushing all the registers to the stack, which basically saves them. At the end, you can then pop them back off. Just keeps doing that, just storing or zeroing out registers, or pushing or saving register and then zeroing it out. Let's go on for a bit. Okay. If you look at the registers now, you can see that pretty much all of them are now zeroed out, except the ones that were used as an argument to the syscall, which in this case is rax, which contains the syscall number, RIP, which is the instruction pointer, and RSP, which is the stack pointer. Everything else here is now 0. Okay, so now we get to this point. We saved our state. Now we do the do syscall 64, which basically attempts to do a 64-bit syscall and step into it. At this point, I'm just going to type finish to go to the end, because this now calls a lot of other functions and does a lot of different things that we don't really care about right now. So finish just goes to the end of this function. So we're back in entry syscall now, right after executing this. Now just keep stepping through. After a while, you see we're back at the counterpart of what we saw earlier. We're now popping the registers back off the stack. Restoring all the registers. If we look at the register, I believe the stack state should still be in kernel. So yeah, if we look at RSP, this is our current, where RSP currently points to. This is an address that's much too large for a user space address, so this is still the kernel stack. Can keep stepping through. Pop rax, restore our IP. And now finally, pop RSP is still kernel. Do one more step. And now if we look at RSP, it's back to our user mode stack. And then it executes swap.js, which swaps the JS registers. Can talk about that a bit more later. And then executes the sysread instruction, which is in charge of returning back to userland. So execute that. And now we're on the instructions we saw earlier. We're back in our get fit binary we ran. We try to keep running, we get a page fault, and that would eventually result in a sec fault. Okay, so we just walked our single step through a small program. We traced the syscall, saw how it looked. Any questions on what we did? Yeah.
So is that act of pushing and storing registers this kernel's implementation of context switching?
Part of that. Yeah, that's how it like saves all the registers state pretty much. Yeah. Yeah.
How do you tell where is the user space, where is the kernel space?
The kernel space is at the very top of the address space. So the kernel space in this case, you saw the. If you looked at the, actually, I don't have VMF right now. It's a running base GPU. If you look at the address here, for example, in comparison, if you can read it, this is a much larger address. The kernel space is at the very top. I don't know how many gigabytes memory it is. The kernel is at the very top of the memory space, and user space is below it. It's pretty much how it's divided.
Right. Also, VMAP won't do you any good if you have KPTI is in this kernel.
Yeah, I'm not sure if it is, but
And it's 5.4, so it's hard to say.
yeah. Okay. Any other questions? Actually, probably I don't think I disabled it for this. Okay. So that's pretty much, this is how simple it is to debug a kernel pretty much, at least Linux kernel. Windows kernel is, you have some extra challenges, but on Linux is pretty much all you have to do. So let's say you were trying to exploit a driver or interact with the driver and you wanted to debug what it's doing. So in your project, you need to implement the read and write syscalls, for example. In this case, you can then get the address of so you can load your driver that you wrote into memory, then get the addresses of the functions of the driver, and then do the exact same thing where you set a breakpoint on it and then run your user space program, and once it hits that function, you trigger your breakpoint and you can single step through your driver functions. Okay. Are we good on debugging? Okay. Next, some important files and instructions. In terms of files, I just have this list right now, /proc/k_allsyms. This file pretty much lists all the symbols that are loaded into the kernel and their addresses. The main uses we have for it is at the very top, you can see the base address of the kernel, or the text section of the kernel. And at the very bottom, you can see the functions that were loaded in by the last loaded kernel module. So in this case, just continue. So let's delete our breakpoints. Continue. Let's look at the first few entries. And we can see that the kernel text section starts at this address, for example. If we loaded in a driver and wanted to debug the driver, you would instead use this with a tail command, and your driver functions would be at the very bottom, and you could find the address of where your driver function is loaded in. This is, of course, assuming that no protectors like ASLR are enabled. Next, there are two instructions that I would like to briefly mention that you probably haven't seen before. First, the swap.js instruction, which you just saw. It pretty much swaps the GS register between kernel and user mode, and the GS register is pretty much like a mini constant, or kind of like it points to a region of memory that the kernel uses to store some metadata or some important pointers that it uses. So swapping the GS register between kernel and user mode is a quick way for the kernel to figure out some of the current state it needs to start executing. And the iRedQ instruction, it's very similar to the sysredq instruction we just saw while debugging, and pretty much just performs the actual swap to user mode. It requires a couple of registers such as RIP, CS, rflags, SP, and SS to be set. Okay, so how do kernel bugs look? They're actually pretty much the exact same as userland bugs. You have the exact same buffer overflows, you have your use after freeze, you have double freeze, you have Yeah, I guess those are the main ones. You also have integer bugs, of course. All of these bugs that exist in userland also exist in the kernel. And the mitigations are actually, in a lot of ways, very similar as well. So you have stack canaries, basically exact same as user space. You have a canary at the end of a function that gets triggered if an overflow is there. You have KASLR, which is ASLR just in kernel. You have SMAP, which is basically NX for the kernel. SMAP, which is similar to NX, just that the user mode pages are non-read writable while in kernel mode, so kernel bug can't just write to arbitrary pages in userland. So SMAP and SMAP stand for supervisor mode execution prevention and access prevention, and they can be pretty hard to bypass depending on your bug. Then there's KPTI. This is what Josh mentioned earlier. This separates the kernel and user mode pages while in kernel mode. This was implemented as a protection for Meltdown mainly. Does anyone remember what the Meltdown vulnerability was? We talked about it earlier, a while ago in class. It was one of the CPU bugs we talked about. So Meltdown was pretty much the bug where a user space process could attempt to perform a privileged action, and that would then, because the branch predictor would then execute these instructions, if it then realized that it wasn't allowed to do that, it would then just reset it. With Meltdown, this could be used to leak information from the kernel, for example. So what KPTI does, it pretty much completely separates the kernel and the user space address, or the kernel and user mode address space, so a bug like that can't just write to or read from the kernel anymore. For normal kernel exploits, it's pretty trivial to mitigate, but for Meltdown, it pretty much completely mitigated it. And there's FGKSLR, which is similar to ASLR, just that it does not just randomize the base addresses, but it randomizes pretty much every function. So this has a very heavy performance implication. In this case, you're pretty much randomizing everything, so a lot of addresses have to be dynamically calculated, and this does slow down the kernel a good bit, so it's not on by default yet, I believe, although it is planned. But this makes it very hard to, makes bugs a lot harder to exploit. If you remember, for our user space exploits, if we leaked one ASLR address, we suddenly knew where everything was in the libc, for example, or one stack address, we could calculate all the offsets in the stack. With FGKSLR, a single leak is no longer going to be enough to get all of this information. Any questions so far?
FGKSLR, that sounds like a good idea to me. It makes a lot
But
of
it's
sense.
slow.
No.
It's mostly just performance. People don't like performance decreases, so
Yeah.
it's been in development, but it might come eventually, but it's not there, at least by default yet. If you care about protection on your system, you can enable it though.
Okay.
Any other questions? Okay. Then let's talk about how the kernel exploit might look. This time, pretty much the easiest technique you could do is a red2 user attack, which is pretty much the equivalent of the red2 shellcode we did as one of the very first exploits we did in this class, or in the user mode at least. This is mitigated by pretty much all the mitigations we previously mentioned, the main one being SMEP, which adds an X to the kernel. So in that case, this would no longer work. Pretty much the goal is to increase the privilege level of the process while you are in kernel mode, and then executing system bin sh in the user mode process to then spawn a shell as the root user. So for this, there are mainly two kernel functions that are mainly used, the commit creds and prepare kernel creds. And this is pretty much set up by, first you call prepare kernel cred with an argument of 0, which stands for the UID that, and then creates, or then it returns a value. And this value then passes to commit creds, and that then commits the struct that, or the user struct that prepare kernel cred return, it then commits that to the current process. And you can basically use that to set the current, or give the current process root permissions. So the basic idea behind the read-to-user technique is you store shellcode in userland, and then you use some form of kernel buffer overflow to corrupt execution and jump to your shellcode, or jump to your shellcode that then changes the privileges and executes system message. So when, I guess not. Any question on this so far? Yeah.
So returning from the kernel to a process, where the process is the thing we've attacked?
When you're interacting with a driver, for example, you're writing a small C program. For example, you might write to read a file, and that might trigger a driver. In this case, in the C, you exploit a bug in the kernel, and in the kernel, you then call commit creds and prepare kernel creds to set the give the process root privileges. And then you return back out of the kernel to the process, and then the process can just execute system -h, and you have a shell, a root shell in this case. Okay, well, we can look at the code of how such an exploit might look. Okay, can you read that? Yeah. Okay. So there are a couple of things we need to do. So, as I mentioned earlier, this exploit is reliant on returning to userland to then execute your shell. So you can't just crash in the kernel, you do actually need to successfully return back into userland. So the very first thing you usually do, or if you remember the iRedQ instruction, I mentioned that it requires RIP, CS, rflags, SP, and SS to all be set correctly. If they aren't, iRedQ is not going to be able to successfully return to userland. So the very first thing we do is pretty much just write some inline assembly that then saves off these registers. So it moves the CS register into user CS, SS into user SS, RSP, and so on. So basically it just saves all, while we're still in user mode, it saves all these registers into some global variables we have defined here. This is pretty much just like, so when we try to return from kernel space, we have these values and can just restore them. And then iRedQ is going to succeed and return to userland. Next, we call open process. This opens the device that we're trying to interact with the vulnerable driver in this case. So in this case, this might be the proc/threat-to-user device, which is potentially vulnerable to such an attack. And it just sets FD to this, so we have a file descriptor to the device we're trying to interact with. Next, you can pretty much ignore it. If cookies are disabled, you don't have to do this. In this case, assuming that cookies are enabled, you might first need a leak. So in this case, if the driver, for example, has an out-of-bounds read, let's say it only has a buffer of size 40 and you try to read 60 bytes from it, then some index in this buffer might go out of bounds and could leak the cookie off the stack. Pretty much exactly like user space, just that in this case you're writing your exploit in C. I don't have the kernel module right now to show how exactly this bug looked, but pretty much just the kernel module allocated or had a small buffer on the stack, and then when read was called, it read from this buffer, and in this case we read 60 bytes. The buffer held less than 60 bytes, so if we access the fifth index here, it goes out of bounds. Does that make sense? Okay. And with this, we could, for example, leak a cookie. We could also leak kernel ASLR, pretty much whatever we want to leak off the stack. And next, we call this function, which once again uses the out-of-bug write bug. So it sets up a payload, which in the fifth index, in this case, it places the cookie. Then in the seventh index, it puts a pointer to the escalate privileges, and then it sends the payload, in which case it just calls the write syscall on the device, on the vulnerable device, using the payload, which in this case is too large and causes buffer overflow in the kernel, in which case the cookie the payload of 5 would overwrite the stack cookie on the stack frame, and payload of 7 would overwrite the return pointer, exactly the same as a user mode exploit would do it. And if we look at the actual escalate privileges function, once again, pretty much just some inline assembly. Pretty much the only thing this does is setting up the calls I mentioned earlier, where it first calls prepare kernel creds with argument of 0. Then it moves the value returned from prepare kernel creds into RDI and uses it to call commit creds. And it does the call here. Then it calls swap GS to restore the GS register. And then it restores all these values I previously mentioned, the SS register, the stack pointer, the R flags, CS register, and RIP register. And then it calls iRedQ. And this basically then performs the return to userland. And our user RIP, we set to the getShell function. And this getShell function is pretty much just a small wrapper that pretty much just executes system sh. So pretty much what we're doing is we get our cookie leak. Then we call the clone function, which uses a buffer overflow to both overwrite the cookie and the return address. So exactly same as our userland exploits. When the kernel tries to return, it's going to then return to our escalate privileges function instead of what it was meant to return to. This escalate privilege function calls commit creds with prepare kernel cred to give the process root permissions. And then it performs the routine that is necessary to return to user space, and with the RIP register is set to the getShell function, which just calls binsh. Any questions? Does it make sense kind of how this works? Or are people just confused? Okay. So just to recap, we pretty much start by saving off the state. Then we open the device used by the vulnerable driver. Then we can, for example, use an overflow on the read syscall to leak ASLR and Canary. We can use an overflow on the write syscall to overwrite the return address with the address of our escalate privileges shellcode. And the shellcode then calls commit creds, and then I guess I forgot a 0.6, and then returns to user space into our getShell function. Yeah.
Can you just call read and write on any driver or device? Like
Yes.
Just like arbitrarily call it on it, and it'll just work.
So we talked about that last time. So pretty much all files on your system have a driver that is responsible for supporting it. So if you try to read or write from the file, this driver gets called to handle your read and write calls. So in this case, we would be assuming that we maybe create some custom device. We write a vulnerable kernel driver for it that has these bugs. Then we try to read and write, and then register that kernel driver for this device, and we then try and read and write to that device. This kernel driver attempts to catch these read and write syscalls, and if it has a bug, we can exploit it. Does that make sense? Anything else?
I mean, to answer your previous question, I think I'm just confused, but I think it's just going through the code and the lecture in slow motion.
Okay. Should I go through it again?
No, it's fine. It'll take too long.
Okay.
Thank you.
Well, I'll assign a reading that goes over this in a bit more detail. I'll post on Moodle after class. So if you're confused, maybe they can look at that as well. That pretty much walks through it step by step as well. Yeah.
So what does the user space get shell function do? Is it at all required for this, or is it just you need to return to the function so that the shell code is actually executed in the kernel?
This is pretty much all the get shell function does. You just return to userland, and in this case, if you want a root shell, at this point you just have to return to some valid user space address space. So in this case, I just chose the get shell function, which just spawns a shell for us, which in this case is a root shell. But if you didn't need a shell, you could also execute any other code in here and have that executed as the root user. So this pretty much relies on setting the permissions of the process that invoked the driver to the root user, and then returning into that process, and then in the process you have root privileges. And then you can do whatever you want. In this case, we just spawn a shell, so we have a root shell. We could also just write to a kernel config file here if we chose instead of spawning a shell. Okay. Any other questions on this? Okay. Then let's talk about how kernel, or I guess quickly before we move on to heap bugs. So this was assuming that all mitigations were disabled. What do you think? How do you think could we edit our exploit if the SMAP mitigation was enabled, which is basically the kernel mode NX? How could we bypass this? Given that we have the same buffer overflow. It's very similar to user mode. What would we do in user mode when NX was enabled? Yeah.
Is it kernel raw?
Yep, exactly. So in this case then, if you look back at the code, he said this was pretty much the main shellcode, which in this case we can no longer use shellcode because it's no longer executable. So in this case, instead of this shellcode, we would have to find ROP gadgets that pretty much do this code for us. So we would need to find ROP gadgets that call prepare kernel cred, call commit creds, and then push all these registers, which sounds like a pretty long ROP chain, but if you look at the kernel binary, this might take a second. And you can already see at how long it takes. So yeah, this has about 6 to 7 million instructions. So you have a lot of ROP gadgets to choose from in this case. So you can generally get this, even if the ROP chain is a bit long, you should still be able to get it done fairly easily. NX enabled, the only thing you change here is instead of writing the shellcode, you write a small ROP chain. Exact same as user mode.
And can that ROP chain be found by using ROP gadgets as we had been before?
And this time you just use it on the giant kernel binary. We should just use once and save it to a file and then grep through the file because every ROPR run takes like 5 minutes. But yeah, pretty much it's the exact same idea. In a lot of ways, at least the basics of kernel exploits are the exact same as user space, apart from like some small differences that we saw so far. But the overall ideas are very similar. So with the stuff you've learned about user line exploitation in the course so far, you can get into kernel exploitation fairly easily, at least into the basic ideas of it. There are concepts that get a lot more complicated, especially if you look at the most common kernel vulnerabilities, which are race conditions. That then require you to know a lot more knowledge about how the kernel works, what might trigger a race condition, different kernel functions that you can use to extend the race window, and so on. But for basic kernel exploits like buffer overflows, this is pretty much extremely simple, exact same as userland.
How would you get race conditions within the kernel specifically? Is it normally multi-thread?
Let's say you write 2 user space binaries, and both call on the driver to do something to interact on a device. Then both of these drivers will run at the same time, and if they aren't properly parallelized, you'll have if they both try to access shared memory, for example. Let's say you have a structure that saves information about this device, and they both try and access it, you may have a race condition.
Makes sense.
And in kernel space, there are a lot of race conditions.
Because then it comes down to sort of which one is scheduled first, so to speak.
Yeah.
Okay, that makes sense.
And that's probably the most common kernel bug, alongside probably use after freeze as well. Buffer overflows are a lot easier to prevent usually. Yeah.
I'm guessing there's no pound tools. I'm guessing there's a bunch of libraries for C, so you cannot use the function you use or.
No, you just do it in C pretty much. Windows kernel exploitation in C++ and Linux in C. Don't ask me why, but that's just how people do it.
Yeah, that's what the kernels are written in.
That makes sense, actually. Yeah. Any other questions on this so far? Okay. Let's look at how a heap bug might look. This is actually very different than our user space heap bugs, but a lot easier, to be honest. In user space, we needed to fully understand the kernel allocator. We needed to manipulate the heap metadata and manipulate the chunks to give us back corrupted chunks and so on. In the kernel, it's often a lot simpler. So it pretty much relies on allocating existing kernel structures into memory that we control using a heap bug. So let's say we have a use after free. We have this chunk in kernel memory. We free it, and so just to mention real quick, the kernel uses also uses different types of free lists. They are different, very different than the ones implemented by malloc, but the basic idea is the same. That you try to recycle kernel chunks that have been previously freed. So in this case, let's say we have a use after free bug. This chunk here is freed, and we can still access it at this point. So in the kernel, there are a lot of different interesting structures, and depending on the size of the allocation, there's a good chance that you might be able to get the kernel to just allocate one of these structures into this field and then overwrite it. So let's say you have this free chunk in kernel space that you can still have access to via use after free bug, and then you call a kernel function that allocates that tries to allocate a chunk or a structure that has a function pointer. And this structure might be overlaid with this kernel chunk, and then a function pointer might be written here. Then using your use after free, you can overwrite the function pointer, and when this function pointer is called, you have code execution. Any question on that? Or none of that makes sense? So you're pretty much just not trying to corrupt the heap metadata in this case. You're just trying to, you have this arbitrary chunk in memory, and you try to get the kernel to allocate one of its a data structure that would benefit you into that allocated piece of memory that you can still control. And if that, for example, has a function pointer, the kernel would then probably call the function pointer eventually, and you could get a shell if you corrupted it. So let's look at how such an exploit might look.
To do that, you need to know the structures of the things the kernel would read into that chunk, right?
Yes. There are some lists that CTF players mostly have set up of kernel structures that are useful for things like that, of different sizes. For example, the one that this exploit uses is the, actually look at the structure first. So this is the struct that I am using in this exploit, for example. So you free this. So the idea of the exploit that I'm about to walk through is that you free this chunk of memory, and then you ask the kernel to allocate this chunk, also in a bit, or this structure, and you try to have this structure overlaid with a heap chunk that you have control over. So if you look at the structure, it has a function pointer in the first position, for example, also in the next use. So then once you corrupt it, you can then corrupt one of these function pointers and get code execution. Or similarly, these function pointers might or would instantly be populated. So if you have a read after free bug, you can then read those function pointers out and bypass kernel ASLR, for example. So the main list for that. This is when you start getting into the realm where English resources aren't sufficient anymore. So this is from a very good CTF player. He set up this list here that just contains a couple of different kernel structures, like the sec operation structure that we just looked at. and these are of different sizes. So let's say you have a heap chunk of size 0x20, or a different exploit, you might have one of size 0x40. You would need different structures because the kernel, also similar to the userland, uses size fields to allocate from its bins. So these are a couple of different structs of different sizes that all have either function pointers or pointers to memory. That if you corrupt them, you can leak out addresses or overwrite addresses, and you kind of just set up a small list of useful structures for that here. Alternatively, you can also just browse the kernel source and look for structures that you think are interesting and that you could use in your exploits. But this is a pretty good list to get started on, first of all. If nothing here fits for the bug you're looking at, then you might have to dive deeper into the kernel source itself. So yeah, any questions so far? Okay, so let's look at the exploit. It starts the exact same as before with saving the state, which our goal is still to return to userland after our exploit, so we need this state. And opening the device, which in this case is /def/challenge, whatever. And then we call the own function. This function then allocates 3 chunks. It does this using so this was an exploit for a CTF challenge I played a year ago or something that had a kernel use after free bug. And it was pretty much, if you've looked at Project 5 yet, you might have seen kind of, I believe Project 5, the non-FTP server one, had kind of like this heap node structure that is very common in CTS, where you have a create function that allocates a chunk on the heap, an edit function which you can edit a chunk on the heap, and a view function which you can read out data from the heap. This kind of implemented in this kernel as well, kind of a heap node challenge, using the IOCTL syscall. So in this case, to interact with the kernel module, we call IOCTL, pass it an argument that tells it, for example, the 0x1337 argument in this case, told the module that it was supposed to allocate a new chunk using the length field we passed to it and the name in the buffer struct, or the request t buff struct, which is this structure. And yeah, the edit one, exact same, just we passing 0x1338, which indicates that we want to edit. View the same again, and this was simulated kind of like a banking software. So it also had a transfer where you could transfer money from one account to another with this value. So you pretty much just populate the struct, pass it to IOCTL, which has a switch statement depending on which argument you pass to it. It does one of these heap node things. Not that important. So looking at the exploit, so we start by allocating 3 chunks. All of these pretty much just populate a buffer on the heap. And then we start by freeing 2 of them. So assuming we have use after free vulnerabilities, we just created 3 chunks. And then this and these 2 are both free. Okay. Anyone have an idea what this little for loop, what its purpose is? We're opening a very specific file here, /proc/self/stat. I don't expect you to know what exactly that would do, but do you have any idea what the purpose of this might be to just allocate a bunch of stuff here? Yeah.
It looks like a device that describes the state of a whatever process is calling it. You're opening it read-only, and you appear to be trying to write through a specific buffer. I'm trying to remember.
I'm more going for what purpose does this have for our exploit? Yeah.
Is it just to give you a bunch of chunks to work with, so when they're freed, it's going to be one of those?
Yeah. So in this case, when you try opening the /proc/self/fstat, this file is a special file that has a specific driver for it, or at least specific driver options. So when you try opening this file, the sec operation struct that I still have that open. Yeah, this struct here is allocated for when you open this file. So in this case, we open this file 0x100 times. Each time this struct is allocated, and since the kernel works in a very similar way, then the user space heap allocator, we're kind of banking on that one of these 0x100 allocations would get allocated into one of our free chunks. So pretty much just, this is called a technique called heap spraying. it's usually less at least on Linux userland, it's not that popular. It's very popular when you do Windows exploitation. We're pretty much just allocating a bunch of stuff on the heap and hoping that something lands where you're trying to get it to land. So in this case, each of these open calls allocates this structure we mentioned earlier because it's being run in the specific file. Next here we use the useApp for free on the first. So in this case, we're trying to get it into this chunk mainly, or into both, I guess. And then we use the leak function on this chunk, which these two. So these two chunks, the 0 and 1 chunk, both of which we freed earlier, the first and second, should both now be overwritten with a sec-op structure. So we now call the leak function, which pretty much just tries to 0x1339, which was the view one. This pretty much just tries to read from the chunk and calculate the base address of the kernel. This was actually compiled with kernel ASLR. So we're bypassing it the exact same with bypass user ASLR. We leak an address, which we do here by reading into our buffer. And then the buffer pretty much just reads in the data from the structure. And in this case, the balance field of the buffer points to an address that we can use. And we use that to calculate the kernel base. Does this make sense? So we have these overlying structs. Then we try to read from it. So we call the read syscall or the ioctl read command to read this into the buffer that is returned to userland to us. And then this buffer then contains the data that was stored here. So we can then read data out from this buffer, which in this case, since it had some function pointers, was an address that we can use to bypass kernel ASLR. Everyone good on that? Okay. Next, we allocate a ROP chain. So even for heap exploits, we are still going to be using ROP chains in this case, unlike the userland heap exploits. So in this case, this maps a chunk at some address, and then fills this up with our ROP chain. So these are all kernel base plus set flag, and all of these are values that I hard coded here. So adding kernel base plus these addresses then results in these gadgets that are listed here, or for example, the prepare kernel cred function or the commit creds function. So we built this ROP chain here that is pretty much just written to this address. This address in specific was chosen because in this case there was a stack pivot gadget that pretty much moved this address that is listed here into ESP. So our goal is pretty much in this case that we corrupt. So in our exploit, in this case, first of all, we start by setting up some buffers. Once again, these pretty much just serve to set up a buffer properly that it overlaps correctly, or just calculating the correct addresses. This is the next main part, where we pretty much call read on all of these FDs that we receive from opening /proc/self/fstat, and executing read on it executes one of the sec operation struct's function pointers. So we read all of them, and once we hit one of them that we overwrote with our corrupted pointer, it would then try to execute our corrupted pointer, which points to this gadget here, which moves, which basically is a stack pivot gadget that pivots the stack to our ROP chain, and we then execute this ROP chain, which does the exact same return to user as we did before. Okay, this was a lot, and you don't need to understand everything, but do you understand at least the basic idea of how these heap exploits look in the kernel? So in this case, the main idea I'm trying to give you here is you're not, first of all, how these kernel exploits might look, and second of all, that when you're exploiting kernel, the kernel heap, you're usually not overwriting metadata but rather you're just trying to get a kernel struct with some function or memory pointers to overlap with your vulnerable or with your chunk that you have access to, and then you can read from these chunks to leak ASLR or cookies or not cookies because they're on the stack, to leak ASLR, for example, or you can write to these structs to overwrite function pointers or memory pointers that you're writing to get arbitrary code execution or arbitrary read or write. Okay. Any questions on this?
How would you go about debugging an exploit like this besides running it 100 times and seeing if it works? Given that it seems a large crux of it is waiting on the chance that a allocated chunk is eventually used by the kernel. Are you given any guarantees to that end, or are you just sort of...
This is why we're doing the heap spray, where we're allocating 0 to 100 chunks at a time, and this basically guarantees that one of these chunks is going to get allocated into this free chunk. You can also make this a lot more if need be, but given that nothing else gets allocated into this before we execute this loop, which is very unlikely considering we free it twice and then immediately do this allocation, one of these should overlap with this chunk.
That makes sense.
That's kind of why we're doing so many, not just one allocation. In theory, we could remove this entire loop and just do it once, and in a perfect world, this would get allocated directly or twice, I guess, for these two, and these would get allocated directly where we want them to. In reality, a lot of stuff is happening at the kernel. These might get, some other structs might be allocated, for example, so in this case, we're allocating a bunch of them and hoping that 2 of them land exactly where we want them to land. That's kind of the idea of heap spraying. Not always 100% reliable, but it often works pretty well. Any other questions? If not, we're probably going to start with the fuzzing content.
Okay.
15 more minutes. Any more questions on kernel? I guess with that, we're then concluding kernel. We unfortunately don't have much time for all the remaining topics. So for this course, we chose to invest most of the time on stack exploitation topics, mostly because those are first what you have to start with, and number 2, because they're the most relevant. Or heap exploits are very relevant, but their difficulty usually comes from experience, less so than techniques. So with stack introducing techniques such as shellcode or ROP was very important, so we decided to allocate most time to that, and then a lot less into heap kernel and fuzzing stuff. So we don't have much more time to go into this in more detail, but yeah, this is pretty much our content for kernel then. If you have any question on any of this, before we move on to the next topic.
I have a question over with Al.
Yeah.
Can you hear me?
Yes.
Are you muted?
On my Zoom I am, but...
No, I'm not coming through. Oh, okay, sweet. So I know you touched on it, but could you go over like the point of kernel exploits? Like, is it just privilege escalation? Like you already have user mode, and then you can do the kernel exploits to get root permission, or are there other uses? Like, what's kind of the high level point of kernel exploitation?
I just realized I forgot to totally touch on the point of applications of kernel security. So first of all, talking about kernel exploits. The main purpose is usually privilege escalation, although there are instances where you might have a bug in a network driver, for example, or Bluetooth drivers, which are very popular to be buggy, or printer drivers that have remote implications as well. That would then give a remote root exploit, which is very dangerous. But most kernel exploits, I would say, are just privilege escalations because there's just a lot more surface to attack there than the remotely accessible kernel surface. In terms of other applications of kernel security, number 1 would be things like rootkits. This is mostly used from either things like antiviruses or anti-game cheats, or malware. So there's 3 ones. And for the purpose of malware or AV and anti-game hacks, they're usually not referred to as rootkits, but they're pretty much the same thing. You load something into the kernel that might, for example, hook syscalls and check what these syscalls are doing and maybe corrupt what they're doing. Should have an example here. Let's see. Okay, so So I just loaded, so this is a small rootkit I wrote a while ago. So I just loaded this into the kernel as a kernel module. And in this case, I implemented a couple of simple functions. One of them, we make a direct directory and go into it. So this is an empty directory right now. One of the features that the kernel, or this rootkit supports is, for example, to hide files that start with specific names. So the touch command is used to create a file. If I create a file, use ls, we can see that the file is now created. But if we create a file that starts with AAA, and look now, this file does not exist. Or at least it's not displayed to us. We can also use ls-la, check for hidden files. This file just is not displayed to us. Why is that? In this rootkit, for example, I hooked a syscall that is called when you're interacting with the file system driver, and it checks for any files that start with AAA and hides them. You can see how malware might be very interested in using rootkits. It can use it to, for example, hide its files on your disk, so any user mode process that tries to query the disk for malicious files cannot see them anymore. It can do the exact same to hide processes from process lists. It can change or hide network traffic. So for malware, rootkits are very dangerous because they have a lot of control over the system and can basically manipulate the output that forensics tools might give a malware reverse engineer, for example. The same applies for game cheats, for example, or anti-game hacking measures. They often are implemented in the kernel as well, so they have more access and can better monitor what game hacks might attempt to do, for example. Especially, and yeah, exact same applies to antiviruses as well. So this is one both offensive and defensive application of kernel security. Any questions so far? And then I guess one last one that is a lot less popular but also exists is on embedded devices. They often use, or a lot of embedded devices nowadays just run Linux. But sometimes you can also find embedded devices that do not run Linux and are pretty much just one giant kernel. In this case, if you want to get a shell on this device, for example, or have any form of interaction with this device, maybe set up a GDB stub in it, you might not be able to just load a user, or if it had Linux, you could just load GDB onto the file system and be able to interact with it remotely, for example, or a reverse shell binary. This might not be the case if you have an embedded device that's much just one giant kernel blob. In that case, you might instead have to write a driver for this kernel that you can use to interact over the network with it. That driver then opens up a port, and you can then interact with this driver to set up a debugging environment on the embedded device, for example. There's another application, but a lot less common and usually not worth the effort, but it is a possibility. There are probably more applications of kernel security. Those are the three main ones I've come into contact with. But yeah, any questions on this?